Okay. Hi everyone. Thank you for joining the ISDSA workshops. And it is my great pleasure today to introduce our speaker, Dr. Steven Boker, Professor of Quantitative Psychology at the University of Virginia, where he directs both the Human Dynamics Laboratory and the Life Academy. Dr. Boker is an internationally recognized expert in structural equation modeling and the dynamical analysis of longitudinal data. Dr. Boker's innovations include differential structural equation modeling and latent differential equations methods for testing and comparing dynamical systems in mixed longitudinal and cross-sectional data, as well as the windowed cross-correlation method for detecting non-stationary relative phase in multivariate time series. He also developed the RAM-path, a path analysis method now built into many modern structural equation modeling programs. Dr. Boker has also contributed to several statistical software and is one of the original developers of OpenMx, the open source structural equation modeling software used worldwide. His applied work spans fields such as developmental and clinical psychology, and he has authored more than 150 publications. Dr. Boker is the winner of 2024 Distinguished Researcher Award from University of Virginia and the 2020 Southwell Award for Lifetime Achievement in Multivariate Psychology. He's a fellow of both the American Psychological Association and the Association for Psychological Science. In this workshop, Dr. Boker will give a lecture on structural equation modeling using OpenMx. If you have any questions, please feel free to put them in the chat as we go. And now I'd like to turn it over to Dr. Boker. Thank you very much.
Hi, welcome to the workshop. I hope you enjoy the time here. So please feel free to put questions in the chat, and then Zhang Yu is going to alert me, and maybe he might unmute your microphone so that you can say the question out loud, so I don't have to put on my glasses and read the tiny print over here on the computer beside me. So without further ado, we're going to go through several levels of complexity here, starting with the very basics, because I don't know exactly, who is attending this workshop and what your level of expertise is with structural equation modeling. So I'm going to give you a brief overview, background, and then we'll move into two more advanced techniques, the products of variables method and multi-group modeling. So without further ado, we're going to be using OpenMx here. I'm one of the developers, original developers of first the MX package and then when it became OpenMx. And it's, basically it's something that's running in R. You can download it from CRAN if you like. That's probably the easiest way to get it. Also, then there's this web address, this site, openmx.ssri.psu.edu, and this is where we have our forums, and you can ask questions. You can also download the software there, and that version has a different optimizer as one of the options, optional optimizer, which is not allowed for us to put on CRAN because it's not totally open source. But otherwise, the OpenMx package is, well, it has lots of different methods. We're going to be going through the multi-group methods and products of variables methods, but it allows a whole variety of other complicated but powerful techniques. So the idea behind OpenMx, when we were designing this, we decided that we wanted to have a package that people could use uh, as to do whatever they wanted to, that would allow as much as we could, instead of structuring um, the the way that you would think about SEM. We tried to make it as open as possible, so as flexible as possible. And so our philosophy, we came down to this, that we would not uh, we would not worry about, or when questions came up about whether it was better to have a more powerful, flexible program or a program that was easier to use, we tried to make it as easy as we could, but we always came down on the side of more powerful. And what that has meant is that the scripting language the scripting that you can do with it is very deep, and it's flexible. Um, and we've tried to future-proof this so that the program can grow into the future. We are uh, in in the middle of transitioning to a nonlinear version of structural equation modeling, which is uh, a difficult thing to do. But we've tried to make the language as flexible as we could, and and allow for this extension into the future. But there's good parts and bad parts. The best part, I think, as far as I'm concerned, the best part is that all the choices that you make are exposed in the script. We try not to hide anything that we're doing behind the curtain. If you make a choice, it should be there in the script. And what that means is then when you send a script to somebody else, or you're reading somebody else's script, you know exactly the choices that they made. There's not sort of like magic stuff happening in the background. So what that is good, but it means that the scripts can be relatively long. They're longer than you would expect from other packages, because other packages are doing things automatically. Well, that's because they chose to make a program that's easier to use rather than one that exposes everything. So these are the choices we've made. We've also made the choice to make this entirely open source, with the exception of this one optimizer, which we have a license to distribute, but we don't have a license to distribute the source code. Everything else in OpenMx is entirely open source, and it's Apache 2.0 licensed. That means that you can use it. You can use our code for any purpose you'd like. It's all available on GitHub, and you can download it and use it, modify it, change it into whatever you want. And the idea here is just the same as the scientific model. We would like to, we ask that you acknowledge our work if you use it in a package of yours. But other than that, we're not asking for anything. So here's the way that OpenMx is structured from the 1,000-foot level. There's a part of it that's in R, and we chose to use R so that R has good, scripting. It has good graphics, pretty good data handling. When it gets to be large data sets, maybe it's not the greatest, but it's pretty good data handling. and it's open source. Um, so that's what the user sees. The OpenMX user sees the R scripting. Well, what's going on is the R scripting is taking what you ask us to do, and then it sends it to the backend, which is a C++ backend written for speed um, and memory management. And the C++ runs fast. Well, sometimes you can build a model that's really slow, but it runs much faster than R. And then the results are sent back into R so that you can see them. That's basically what's happening. So when you ask for MX run, what's going on is it's taking all of the data structures that you've built in R and sending them to the C++ backend for optimization, and then that comes back. So how did we write the R scripts? Well, what we did was we defined functions in an object-oriented manner. That is to say, every time we have a data object, say MX model is a data object, there is an MX model function that is a constructor for that object. And so when you call a function that says MX model, what you're creating is a structure, a data structure that is an MX model. When you call MX matrix, the MX matrix function, it's creating an MX matrix. And these are somewhat different than normal matrices. We'll get into that in a moment. And all of these data structures then packed into a model, and the model is sent to the backend. Okay. Next, naming. When you put names or in a label, that is to say, you can name various things in OpenMX. You can name each of the structures, say an MX matrix, but also labels for any cell in any matrix can have a label. And when you make a label, say maybe George, that is unique. That is then the address uh, of all representations of George. So there's only one George in a model if you name something George. Um, Even though you use that word many times, if you use it many times, then you're saying that all of the occurrences in the model, in the optimization process, are actually the same thing. And so they're constrained to be equal. So equality constraints are accomplished by naming things the same. We'll see this in the examples, especially in the multi-group examples. Um, there's two reserved words. One of them is the ONE1, and that is used as the input for estimating means. And the other is data, and that is used for something that is a a method for constraining a path to be equal to a column in your data matrix. And this we call a definition variable. So an MX model. Here,
Sorry
yes.
to interrupt. Dr. Booker, there are people saying that they cannot see the screen. I'm not sure. Is that same for everyone?
Yeah, we still couldn't see it.
Uh, yeah, I guess, but I can see from my
Yours, I can see my screen on the Zoom in here. So maybe the you need to set my screen as what do they call this?
Okay. I think I'll set you as a host. So maybe that will work.
Yeah.
Sorry about that. So is that does that work for everyone?
Okay.
Oh, okay, great. Sorry about that.
Well, sorry. And I was going, okay, well, people can read the screen, so I won't say what's on the screen.
Uh,
So I hope it's this hasn't been too mystifying.
so this workshop will be recorded. So if you and it will be shared to the participants later, so you can check the feed maybe
Right.
later.
Yeah, and everybody got the or I hope everybody got the slides that I sent out. So you can go back. But now is a good time to be able to see the screen. Um, so let's talk about the main data structure in OpenMX, and that is the MX model. This is sort of the container for everything. All of your other data structures and functions go into this. So a model has a name, and it always has a name. Um, uh, if you create uh, if you create a new model, you must name it. It's uh, that's that's important. Um, so a model must have a name. It has a type. Um, the types we'll be using today are uh, RAM is the main one we'll use, or NA. There's another type that is just okay. So it doesn't know any special functions, but mostly we'll be using RAM. You can also use Lizrel, and it will RAM and Lizrel allow you to draw paths essentially, and as you specify paths or arrows in a diagram, um, it will build the matrices that are required to do the optimization. Um, there are two other pieces, an expectation function and a fit function. Normally software has both of these linked together, but we've split it apart. That's one of the major changes in OpenMX 2. We split the objective function into an expectation function and a fit function. The expectation function is what does the model predict about the data? And the fit function is how are we going to optimize or what are we going to optimize to try and make our predictions as close to the data as possible. And the fit function then will return a value that tells you how poorly your model fits. Your model could fit exactly, in which case that's probably due to the fact that you have 0 degrees of freedom. But if it doesn't fit exactly, then here is the way that you can test statistically how poor the model is fitting. There's data, and almost everybody these days uses raw data. It's what I recommend everybody use. But there are methods for covariance and correlation data. Yeah. There's also optimizer options. So when you ask for an MX option, it's attached to a model. So this model then would have, say, a default optimizer. Um, it also has some output, and there's actually a lot of output. But on the left over here, we have other structures. MX matrices, we'll talk about in just a moment. Algebras, so you can construct an algebra that is optimized at the same time as the model. Constraints, you can make sure that constraints are kept while you optimize. And then this is where things get really interesting. You can also put another MX model inside an MX model, in which case we say the first MX model is a parent, and then there's a child model. And children can have children. So you can have a complicated hierarchical structure of models that all get optimized simultaneously and come back with one function value. So the main thing that's in a model is an MX matrix. And when you ask for, say, a RAM model, 3 different matrices, MX matrices, are created: an A matrix, an S matrix, and an F matrix. And inside an MX matrix, we have types. An MX matrix can have different types. And then there are tables, just like you would think of the first one is the values, and these are a table of values like you would normally think of a matrix. But then the exact same number of rows and columns, there's a matrix of labels, and each of these is a named. You can optionally, you don't have to, but optionally you can name any cell in the matrix so that either it prints out pretty or so that it's constrained to be equal to the cell in some other matrix. You can, the next table is a table of values that are free, and that is either true or false. Is it free or is it fixed? True is free, false is fixed. And then for each cell, you can have a lower bound and an upper bound. So here's the different types that we have. And mostly we'll just use full matrices, but others are possible. So you can put many matrices inside of an MX model. And when you constrain the label, say I call the 1, 1 element of this first matrix C, then the 4, 4 matrix element I've also called C, and then the second matrix I also call that C, then these are all constrained to be equal. And that also applies when there are submodels. So if we have a child model inside the parent model, each of the child models can constrain across models. So this is a way, and we'll do this later in the workshop. This is a way to ask about things like about say, are 2 groups equal in some way? So are the regression parameters in group A equal to the regression parameters in group B? Then you can release those one at a time and see where the groups differ. Also, an algebra can be constrained you can constrain an element in a matrix to be the output of MX algebra, and then you have some real flexibility about how you are going to optimize any parameter in the model. And as I said, you can have each of the models can possibly include other models, and so you can have a whole hierarchy of models. Okay, so I'm done with the architecture section of the workshop or the lecture at this point. Questions at this point before I go on to the next section? Okay. So it looks like two people are waiting in the waiting room. I'm going to admit them. I don't see any hands up. So I'm going to go on. And let's talk now about the actual models, the SEM models. And the way I like to talk about models is I find it easiest to talk about them in a diagram. But we need to have a good understanding of what I mean when I draw particular parts of a diagram, because they are an exact representation of a matrix algebra function that the computer program will be optimizing. So this is a method format called RAM, Reticular Action Modeling, that is due, at least in large part, to Jack McArdle, the late Jack McArdle. And here's the way that it goes. There's squares. These are what's called manifest variables, or observed variables. There's circles. That's latent variables. There's triangles, and those are the constants. Usually it's just a constant that is the number 1. And then small circles with a symbol inside. This is something that is just about to become part of the larger structure here. And we'll see it in the products of variables. And these are called function nodes. This is what we'll be calling them in OpenMx 3. Single-headed arrows are regression coefficients, and double-headed arrows are covariances. And of course, a covariance of a variable with itself is a variance. So this is what they look like. Variance terms, we make a little loop, double-headed arrow from a variable to itself. A constant has no variance. It's a constant. But manifest variables or latent variables can have variance, and function nodes never have variance. They're calculation pieces. So here's a diagram. The sort of thing that we're talking about. We have squares. Those are all observed variables, x1, x2, and y. In this case, this is a standardized model because the variances here on x1 and x2 are 1. And that means that the covariance between x1 and x2 is a correlation. Notice that there's no mean here either. That is to say, no triangle in this diagram. And, it's just bivariate regression. Regression coefficient B1, regression coefficient B2, and some residual. This is the so-called error variance or residual variance. And this number 1 this is a regression that's constrained to be 1. Okay, so how do we do path analysis? So path analysis involves calculating the components of covariance. So you can pick any two variables in a RAM diagram, and if there's a covariance path between them, it's composed of exactly one two-headed arrow, one and only one two-headed arrow, and then 0 or more one-headed arrows pointing away from one end of that two-headed arrow, ending at the variable A, and 0 or more one-headed arrows pointing away from the other end of the two-headed arrow and ending at B. So you can find out what the effects are in your diagram by doing these path tracing rules. So calculating the components of the covariance. And so all of the ways to get between A and B are the sum of each of these covariance paths. Any possible way to get from A to B following these three rules. So let's do an example. Let's calculate the covariance between x1 and y. Well, okay, so here's x1, and a double-headed arrow is pointing into x1, so we'll just start there. Remember, 0 or more, and then we go on the double-headed arrow, and here's pointing away from the double-headed arrow is B1, and that ends up at y. And so we've made it from x1 to y, and that's one of the components of covariance between x1 and y. So that's B1 times 1. But there's another way to get there, and that is through x2. So here's a double-headed arrow. There's 0 one-headed arrows going from the double-headed arrow to x1. And then here's a double-headed arrow, and then that end of the double-headed arrow goes to B2. And so our x1, x2 times B2 is the background effect. So we have a direct effect and a background effect, and we add those up, and that's the total effect between x1 and y, or the total covariance between x1 and y. Let's consider univariate regression. This is just sort of the simplest way, and we're going to calculate what's in the model here. This is our model, and we're going to calculate the model expected covariance between all of the variables in the diagram. And in that way, we can end up with something that we can compare to our data. So the model expectation is going to be this R, and the model fit function would be how do we get the best B and the best VE. So in order to calculate the model expected covariance matrix down here, this has X in the first row and column, Y in the second row and column, and E in the third row and column. So this is all three variables in this diagram. We're going to calculate all of those covariances. So first, we start at X, we end at X, hey, we're done. Just one. And we can just put that into the 1, element of this diagram. So next, let's calculate uh, the variance of E. And is there any other way to get from E to E? Nope, this is the only one that follows those tracing rules. And so we just put VE into the covariance. Let's next calculate the covariance between X and Y. Well, we could start here, 1 times B, and 1 times B, that's calculating X to X, X to Y, and then we put B in here. That's the covariance between X and Y. Now let's calculate the covariance between Y and E, and it's the same way, 1 times VE, we're done. And that means we get to put VE into the expected covariance matrix. Next, what are all the ways to get from E to X? There is no way that follows the tracing rules. There's no way to get from X to E. That's another way to say one of the assumptions of regression, which is that the predictors and the residuals are uncorrelated. And in fact, according to the tracing rules here, we have to put a 0 in this covariance matrix. Finally, let's calculate the variance of Y. How many ways can we get from Y to Y? Well, one way is since we have our double-headed arrow and one end points through this arrow B, and at the other end of the double-headed arrow, we go also on the arrow with the label B. And so we have B times 1 times B. That's B squared. But is that the only way to get from Y to Y? No, there's another way. And that's going through the error variance or the residual variance. And it's 1 times VE times 1. And so the total variance of Y is B squared plus VE. And there it is, our model expected covariance for this regression formula, Y equals BX plus E. Okay, so yeah, this is probably more detailed than you'd ever want to do for a single univariate regression. But it gives you the idea, and once you get this idea, you can use it on very complicated models and see some of the effects that maybe you might have been missing. Well, it turns out that this RAM diagram, it was built from a matrix algebra expression where there's 3 matrices involved. A matrix, which is the total variable by total variable matrix that lets you specify all of the single-headed arrows in your diagram. There's an S matrix where you specify all of the double-headed arrows in your diagram. And finally, there's a filter matrix. The filter matrix, all it does is it allows you to define which of the variables are manifest, are observed, and which are latent variables, circles. And that way you can just pull out the part of the model expected covariance matrix that applies to the data so that you can compare it to the data and optimize. So here's how that goes. If I have my univariate regression here, let's look for all the one-headed arrows. Well, there's a one-headed arrow here from X to Y. So we always start with columns, and they go into rows. And so X into Y is the cell in the A matrix. It's the 2, 1 cell in the A matrix, and we'll just label it B. And then there's also another one-headed arrow, which is going from Y, or excuse me, from E to Y, so that is in the 3, 2 element, and we put a 1 in there. Where are the double-headed arrows? Well, in this case, they're always on the diagonal. They're all on the diagonal. We've got VE, which is going from E to E, and we've got the variance of X, which is a 1. And finally, there's a filter matrix, and that has number of rows equal to the number of manifest variables and number of columns equal to the number of total variables. And in this case, there's just two manifest variables. And once we have this, we can calculate the total effects first by just multiplying A times itself until and keep adding it up. A, or the I, which is the effect of variables on themselves. It's always a 1 in a diagonal. And then the A matrix, the effects that are of paths of length 1, so arrows of length 1, and then add A squared. And then what that does, A squared, then becomes the paths of length 2. When you multiply A times A, if there was a single-headed arrow that went to another single-headed arrow, then that would show up in A squared. And then plus A cubed and so forth. So it turns out that according to this very, very clever way of thinking about the I minus, or this continued expression here, that they found that I minus A multiplied by that continued expression is A plus A, or excuse me, I plus A minus A, plus A squared minus A squared, plus A cubed minus A cubed. And so it all works out to be I, the identity matrix. And any matrix, if you have two matrices that are multiplied together and end up with the identity matrix, then they are the inverses of each other. So the effects here, this big effects matrix that has, who knows how many terms in it, can be expressed as I minus A inverse. So since this is I minus A, then this part must be I minus A inverse in order to make this the identity matrix. Okay, so all of that is to say that if I use I minus A inverse as the effects matrix, the total effects of all the paths, then the expected covariance matrix can be calculated as E times S times E transpose. And so there's our expected covariance matrix. And this is, Jack used to say, the expected covariance, the expected covariances predicted by the model are easy. Yeah, that's right. Anyway, it comes up with the same answer that we got the first time. Why? Because those tracing rules are designed to exactly mimic this matrix algebra. So let's go to our first uh, um, script. So open up univariate raw OpenMx 250711.r. Can people do people have that script, and can you see it? I'm assuming you have R, installed. You could be. I will be using it just in this text editor, but most people use RStudio. I know. I'm a dinosaur. I grew up in an era when there was no RStudio, but uh, we'll go through it anyway. You may have to install this package psych in order to run the script, and hopefully you've installed OpenMx. So the first two lines. Now maybe I should stop. Does anybody have a problem at this point? Are we, I maybe have gone way too slow, but what I've tried to do is to make sure that everybody can follow, even if for some people this may be boring. You may already know these things. So does anybody have a problem at this point? Okay. Well, then let's go through it. The first two lines are to set up for when you have a parallel optimization. It doesn't hurt if you don't have parallel optimization. The CRAN version does not have parallel optimization, and currently our version is out of sync with Apple. Every time Apple updates their operating system, it breaks our parallel system. So we have to make sure that we get that fixed, but it will happen soon. But that means that when you're running a model with raw data, many parts of your CPU can be used simultaneously to optimize. The second piece is just loading the packages and then setting up the OpenMx option to be the number of threads, and you might want to do detect cores -1. Some people like to do that. Mostly, I just want to have things run as fast as possible. Okay. Next, we'll read the data and give it a description and use the psych package to describe the data. Describe the data that we've got. Here, this is a little data set with 500 observations. This is a simulated data set, and we've loaded it in, and we're going to use x1 and y as our manifest variables. And you don't have to do this line. I like to set things up before I start making the model, usually setting up my manifest variables and so forth. And here we're going to use MX model for the first time. And we give the model a name, Unisat. So every model must have a name. In this case, we're going to use RAM. And what that means is we'll use MX path statements. And what an MX path statement does is it identifies which matrix to change, the A or the S matrix, and then which cell to put the change in, and then what you're going to do. So we're going to use RAM. That means our A and S and F matrix will be built automatically. You could build it yourself if you wanted to, but here we're going to be building it automatically with path statements. We'll set up our manifest variables to be the manifests. And then here's our first MX path statement. We're going from the manifest to the manifests. And we're going to connect all of those unique bivariate. So this is drawing two-headed arrows between all of the manifest variables, no matter how many manifest variables you have, and essentially making a free covariance matrix. Next, we do this. Instead of connect equals unique bivariate, we'll use connect equals single to connect from manifest 1 to manifest 1, from manifest 2 to manifest 2, and so forth. So the 1, 1 and 2, 2 elements are connected. Then we have means that will be specified for the manifest variables. And so we draw an arrow from 1, a one-headed arrow this time, arrows equals 1, to the manifest variables. And now for the first time, it's free equals true and values equals 0.1. So we're just drawing arrows from a triangle, the variable called 1, to each of the manifest variables to give the possibility to optimize the means as well as the variances and covariances. So this creates a saturated model. All it is now is a covariances and means for the data that you have. So that's a way to create a saturated model. And then we can run that saturated model. Okay, that didn't take long. And we can get a summary for that saturated model. Here's our first summary. We have the variance of x1, that is to say, from x1 to x1. And we have the variance of, or the covariance between x1 and y. And we have the variance of y. So here's our estimated variance for each of those, and the mean of x1 and the mean of y. Okay, so yeah, this is not the most interesting structural equation model you've ever seen. But it's more interesting than this one, which is called the independence model. Independence model means nothing is connected to anything other than the variances. So we start out with a uni-end, type equals ram, manifests equals, or manifest vars equals manifests here, and draw a path from the manifest to the manifests. Connect equals single, so each one of them is just from itself to itself. So that's the variances. But, and there's means, but there's no covariance. There's no covariance between X and Y. And that is an independence model. It only has 4 parameters. Notice we had 5 before because there's no covariance between X1 and Y. And you'll notice that here's our fit right here. We have 4 parameters. Degrees of freedom takes into account the fact that it is a full information model using raw data. And here's our fit function is 3352. And before, our fit function was 3202. So the model that is fully saturated fits quite a bit better than the model that is independent. Well, why do we do this? We do this because we need 2 values. The independent fit and the saturated fit. Why do we need these? Because any model that you fit is going to be somewhere between the best, which would be the saturated model, and the worst, which is the independence model. And your fit for your model is going to be somewhere in between those. And when people talk about a chi-square value, what they really mean is the difference between the saturated model and your model. But it's also interesting to note what the difference is to the independence model. So how much better did you do than the independence model, and how much worse did you do than the saturated model? And once we have that, we can create the regression model that we were interested in. Now we're going to create a MX path between X1 and Y with one headed arrow, free equals true, values equals 0.2, and labels equals B1. Notice what we're doing here. From equals X1, oh, that's the column in the matrix, in the MX matrix. 2 equals Y, that's the row in the A matrix. And why is it the A matrix? Because this is a one-headed arrow, and so it's going to put a value in the A matrix. Free equals true. Oh, for the 2, 1 element, we're going to set the free to be equal to true instead of false. Everything is false to start out with. And so we're going to set that one to be free. We're going to set the starting value, the value in the values matrix, in the 2, 1 element of this values matrix, in the A matrix, to be 0.2. Labels, oh, the labels in the labels part of the MX matrix, the MXA matrix, we are going to set that to be equal to B1. And now from the manifests, this is a shorthand. if you want to do variances, you can just say from equals manifests, and then that will be all of the that will start at the manifest variable and end at the manifest variable. It always creates variances. So arrows equals 2, free equals true. We're going to estimate them. We'll start them at 0.8 and call them var x1 and var e. Finally, from 1 to the manifest variables, and we'll call this, we'll call these two mean x1 and and b0. Notice that this is the mean of the predictor, and b0 now is an intercept. This is the part of the mean of y that is not predicted by the mean of x. And then we give it our data and we can run it. And now you can see in our summary, we're going to include the saturated likelihood and the independence likelihood. And what that means is, when we run this, we get a summary that includes statistics like the RMSEA and the AIC and BIC, which we didn't get before. So in order to calculate the AIC, BIC, TLI, RMSEA, all of that, in order to calculate that, we need to have the saturated model and the independence model. But notice that our chi-square value is essentially 0. Why is that? Well, because we have the same number of parameters in the model as in the saturated model. So there's no opportunity for misfit, no opportunity for this to not fit. The stronger your model is, the more opportunity for misfit. You know, it's kind of like, it's like playing the game, I can name that tune. And if you can name that tune in with only 3 notes, you're doing really well. Well, what is that? It means that you've not used all of those other notes. And that's what this is like. It's like if you have more, if your model has fewer degrees of freedom than the saturated, then that's like the notes that were left out in the name that tune game. So in this case, you got the whole tune, so of course you could guess it. All right. So there we are. We have it. This is the only time I'm going to go through saturated and independence models because normally you would not use those. I mean, you don't have to build those because we can build them automatically. However, I wanted to show you exactly what's happening behind the scenes when you ask for the saturated and independence models, and you can just ask for them. But sometimes you're going to want to have a very specific saturated model or a very specific independence model because you know something about your data. And so it won't be just the standard. You'll want to have yours. And this is a way to do that. You can set it up. Okay. Well, we can do this same trick with path analysis, going through and looking at all of these paths, and finding that there's or that the correlation between x1 and x2 is this, and you can find out that there's no correlation between the predictors and the residuals, that the residual variance is VE, that there's a direct effect and a background effect for the covariance between x1 and x and y, and there's a direct effect and a background effect for the covariance between x2 and y. And finally, then there's this large amount of things that you can calculate that are the covariance between y and y. And that's b1 squared, b2 squared, and so forth. All right. And here it is all written out. You can also build this into an A, S, and F matrix. This is what OpenMx will build. It will build the A, S, and F matrix. And as soon as you do that, then R equals easy. So, and that will calculate exactly these values again. And then finally, you can filter out the E variable, the latent variable, and get the model expected covariances between your variables. And this is why they call it structural equation modeling, because there's structure here. This is there's the R that you see here in this cell of the matrix also appears in this cell and this cell of the matrix, and also in this cell of the matrix. There's structure to it. In this case, again, this is a saturated model. It's just multiple regression. It's saturated. It has as many parameters as the saturated model. Okay. So I've got we could go to this bivariate regression at this point. This is, this is this is the script that I sent this morning. Or we could take a break. What would you like to do? We're almost done with this section. Anybody? Aha. Okay. How about we take a break? Yeah, let's do it. We haven't been going for quite half the time, but we've got more to do afterwards. Let's take a break. And the bivariate regression script is very similar to the univariate regression script. The only difference is we're using a trick or a wrapper function to calculate the independence and saturated models. So let's take 10 minutes and come back at about 20 after. I'll see you in a bit. Okay, there we go. Okay, we're back. I'm going to skip the rest of this presentation, this piece, because it's just another way of calculating what we've already done. But it's there for completeness in case you're interested. And we're going to move on now to something that probably is new to most of you. Hopefully, we've got enough for the beginners to be able to make it to this spot. And we're going to talk about products of variables. Could somebody tell me if you can hear me? Am I coming through okay? Yes. Okay. Good. Yes. So theories often imply models that require products of variables. And you may have two latent variables that you think have an interaction. You may have a nonlinear dynamical system, which includes, squares or cubics. You may have a multi-level model that has second-level predictors. And each of these are cases where you would want to use products of variables. A latent moderator, even just regular moderated models, when moderation frequently, the way it's used, for instance, definition variables in OpenMx don't allow missing values. You can't use full information to account for missing values in your moderator. And latent interactions are complicated to script. But with this method, products of variables, all of these become very easy. So let's start with a simple regression. But this time, we're going to have the multiplication, the product of x and y as the predictor. So what happens here? Well, the product of the two variables is taken. This is implied by this equation, and then the product of that piece and B1 is taken, and then the result is summed with the residual, and then that is assigned to y. And that implies a diagram that looks a lot like this. X and y are multiplied and then multiplied by the regression coefficient, and then that, as well as the residual, are summed up and added together and assigned into z. Notice that that I'm taking or estimating the mean of x and the mean of y. And this is very important. It turns out that you must have predictor variables that do not have a mean of 0. And I'm sure in your regression course, if you ever studied interaction, using regression, you were told you must first center variables that you're going to multiply together before you enter them into the regression formula. It turns out that when you're going to use this products of variables method, that is not true. In fact, you must have means for these two variables in order for this model to be identified. It's pretty interesting the way that this works. And it's interesting in a way that it took me a year of beating my head against a wall to try and figure out why this method wasn't working when the algebra said it should work. And it was because I was pre-centering these variables before I entered them in, because I'd always been told pre-center the, and it's true. I'm not saying if you're going to use LM to estimate an equation that has, if you have complete data and you're going to just use LM and pre-multiply your variable and two variables together and then put them enter that product into the equation, yes, you need to center the variables first. But here, you need to have those means in order to identify the model. We'll see how that works in just a moment. This products of variables method works by performing three steps. First, the SEM, the model, is transformed so that all variables are represented by a linear combination of some independent, normally distributed variables with known variances. And then from that model, we can compute polynomial representations of those independent variables, and then evaluate the model so that we have the covariance or the variance decomposed of the product, so that product decomposition of covariance happens in this fairly complicated set of steps. There's only 3 steps, but each one of those steps is complicated, as you'll see in a moment. However, we can hide all of this complexity in the back end so that it's all this calculation is done for you, because it is just mechanical. Once you've set up the model, everything else is mechanical. So in the script, you just specify a product node, that is to say, one of these little function nodes, and then draw arrows from and to it, and you're done. So how does this all work? Well, okay. So we have to take an eigenvalue, eigenvector decomposition of the S matrix. And oh yeah, okay, so lots of steps. Then we calculate the moments of these independent variables that came out of the eigenvalue, eigenvector decomposition of the S matrix. And those are known. All of those moments are known. And then that means that we transform the model, the RAM model, into a model where we can calculate the expectations, and then we calculate them. Okay, so it goes like this. The calculation is, there's a few steps of algebra that go on and on, but notice that there's zeros in lots of these areas because the moments for the odd numbered moments are all 0. And so in this complicated algebraic expression, many of these moments are 0. And that means that lots of this stuff drops out. And finally, we get down to the end result. The variance of z can be decomposed into b squared times vx times vy times plus the covariance the covariance of xy and squared and the variance of e. And notice that this covariance of xy squared and b squared that's the only place they appear in this formula. So when we estimate, the b1 could be negative or positive, and it would have the same result over here. The covariance between x and y could be negative or positive, and it would have the same result over here. And that is a problem. And that's where the means come in. So if you do the same calculation with the means, all of a sudden you've got b1 doesn't just appear in the squared piece, but it also appears in an unsquared piece. The covariance appears squared, but it also appears in an unsquared form. And that means that now the sign of the result is identified. So you must have non-zero means for the product terms in order for this method to work. And it's so easy to do that. If the mean of x or y is 0, just add 1 to every element in that whole data column, and it's fine. It will end up with the same result, and the mean will be identified. Or I mean, B1 will be identified. Okay, so here's that. This has no direct effects. It's a bivariate interaction. And here's result of a big simulation. And we have a few spots that didn't come out correctly, and that's when the mean was very close to 0 here. And so when the mean got very close to 0, then occasionally the value got estimated away from, or with the wrong sign for B1. Okay, let's try it out. Let's see how it works. Okay. So we're going to go to bivariate interaction as the R script. And you'll notice that the beginnings, this is all pretty standard in any of the OpenMx scripts that I run. I always add this in case somebody has parallelization enabled. And here we're going to read some data in. There's X, Y, and Z, and there's 1,000 points for each of them. And here's our products of variables model. We set it up as type equals rem. It must be type equals rem in order to get to use products of variables. And we have some manifest variables. And now we have a product variable. And this is called product vars, so product variables. And that's equal to xy. I'm just going to call it xy. That's the name of this node. And that way I can draw arrows from x and y to xy, one-headed arrows, for equals false, so these are fixed to the value 1. And this is always what you want to do when you create a product variable. You want to take the two variables that are going to be multiplied together. There can only be two of them. Take two of them, multiply them together, and you have to use a 1, a fixed arrow, to go from each of those variables to the product node. If you tried to estimate that one of those paths, if you let that be free, then it's unidentified. So you have to fix those arrows to be a fixed value of 1. Now I'm going to next draw an arrow from xy to z, a one-headed arrow, free equals true, values equals 0.1, labels equals b1. And I'm just giving it that b1 name so that it's easy to see in the output. I'm using or I'm estimating the variances of x and y. I'm estimating the variance of z. Notice that for the first time I'm using L bounds here, lower bound, and it's a number, very small number, 1 times 10 to the minus 6th. And I do that so that I don't have a residual variance that's less than 0. The optimizer will stop if it gets very close to 0. And when you estimate models, when I have a complicated model, I always put these lower bounds in for variances, because there are times when there are two solutions for the model, one of them with real valued data, and the other as if the data were imaginary numbers. So the square or the variance was a negative number. And of course, those are, one of those is not an answer we really want. So by putting in a lower bound very close to 0, I constrain the optimization to be within the space of numbers that are numbers we care about. Okay, so finally, here's a covariance between x and y. I'm going to label it CXY. And finally, I'm going to estimate these means, the mean of x and the mean of y. So there it is, our whole model. The good thing about this model is that, or one of the good things about this model, is that if your data are missing at random, that is to say, if you can account for the missingness in x and y, this follows the rules of full information. And that means that that you know, that the estimates are unbiased for missing at random or missing completely at random data. So there it is. All of that algebra happened really fast, and now we have can have a summary of our output. So our estimated B1 was 0.44. Variance of X, variance of Y, variance of the error or the variance of the residual for Z, and the mean of X and the mean of Y. In this case, the mean of X was negative and the mean of Y was positive. That doesn't matter. It was just non-zero. That's all we care about. Okay, now notice that we didn't have reference models, an independence and a saturated model. That is because this is a nonlinear structural equation model. And for a nonlinear structural equation model, it's unclear, at least to me at this point, what the appropriate saturated model would be, because there are more possible parameters than in the covariance data. That is to say, count up the number of degrees of freedom in your covariance matrix, how many cells are free to vary, and that doesn't account for a product of those variables. Okay. Now let's do our comparison. So even though we don't have fit statistics like RMSEA for this interaction model, we can ask, did this value B1, is this value significant? That is to say, could I set it to 0 without loss of fit? So how do I do that? Well, I start with, this is the first time we've done this. I start with the old model, the POV model that I have up here, and I'm going to give it a new name, POV with no B1, and I'm going to set the arrow, one-headed arrow from X, Y to Z to be 0 and constrain it to be 0 and find out how much loss of fit do I have. Oops. There we go. Oh, I have to actually define that model before I do the summary of it. There we go. So now we don't have B1 in this model because I set it to 0 and fixed it there. And we have our function value is 11,811 with 6 degrees of freedom. And over here, 11,729 with 7 degrees of freedom. Well, how do I tell whether that's, is that worse? Well, yeah, it is worse because the fit value is bigger, but how much worse is it? Is it significantly worse? Well, we can use a function called MX compare. And MX compare, you first put in the model with the most degrees of freedom, and then the model with less degrees of freedom, and it will make a chi-square test for that. So we have estimated parameters in the more flexible model, 7, in the more constrained model, 6 estimated parameters. Difference in log likelihood is 82. And yes, that is very unlikely according to the chi-square distribution. And so this test is fair to run, even though we don't know quite what the appropriate saturated model is. We can at least compare these two models. Okay. What happens if they're pre-centered? Oh, yes. Well, we run the same model, centering the data first, and this is many runs with different values for the parameter, and it turns out that yeah, they're not. This is, if it was working, this would be a line right here, and yeah, this is what happens when you pre-center your data. So can you run a model with interaction and direct effects of both variables? Well, no. Why? Because we have more parameters here that we're trying to estimate than there are degrees of freedom in a covariance matrix. So this model has negative degrees of freedom. If you pre-multiply x and y and enter that into a regression formula, well, then there's also this extra covariance between x, y, and x, and x, y, and y, x, y, and z, that give it the extra degrees of freedom. But here we are only dealing with the covariance between x, y, and z, and not the interaction. It's not pre-multiplied. And the reason we would do this is, for this kind of problem, is just because we have missing data and we don't know exactly what to do with it. And full information is a way to deal with that. However, we can have a direct effect and this moderation. So the effect between x and z is being moderated by y. So there's a direct effect of x on z, but there's also a moderated effect of x on z.
Sorry for this interruption.
Yes.
There seems to be a question in the chat asking
Okay.
the difference between the MX compare function and the ANOVA function.
Yeah, so it really is just it's the same idea, but applied to models. So you can give an MX model to this function. All we're doing is just subtracting or asking what is the chi-square, what is the expected chi-square change for 1 degree of freedom of for each degree of freedom between the two models that you're comparing. In this case, we only had 1 degree of freedom. The expected chi-square change at 0.95 is 3.8. So yeah, so it's, there's nothing particularly magic. We're just doing a lookup on the chi-square table. Does that answer your question? Okay. All right. Well, so here's univariate moderation. And we could do this. Notice that in this script, we replace about 20% of the values in Y with NAs and show that it gives an unbiased estimate. But let's move on to where it gets interesting. So now we've got, 3 factors. We've got X, Y, and Z. Each one of these is essentially a factor model. See, here's a factor of 3 indicators for a factor X, 3 indicators for a factor Y, and 3 indicators for a factor Z. And we have direct effects of X and Y on Z, as well as an interaction term. And this model is identified. As soon as you start to have latent variables, you have enough, extra degrees of freedom in your covariance matrix to have an identified model. So this model is identified. And it works. In a large simulation, we can show it works. And once again, the only place it doesn't work is when the means of X and Y, or X and or Y, get close to 0. So let's fit that model. That model is pretty interesting. Now we're getting into where OpenMx is really very useful. So let's go to latent interaction 250711. You notice that we're not talking about a quick mart. We're talking about today's date. Okay. So now we have 1,000 observations, and we have 3 indicators for X, 3 indicators for Y, and 3 indicators for Z. And I start out by, as usual, setting up a vector of names of the indicators I'm going to use from the data set. Notice that we don't have to use all of the data that's in the data set. In this case, we're using every column in the data set, but we don't have to. We can just pick and choose the variables that are of interest to us to model. Okay, so we've got manifest variables. Now we've got 3 latent variables, X, Y, and Z. These are the 3 factors. And we have a product variable. I'm calling it XY again. And I'm drawing an arrow from X and Y to XY. I'm drawing an arrow from XY to Z. This is very much the same as we had before. I'm drawing direct effects from x and y to z. Here's direct effects. We're going to estimate those effects. And now here's our three factor models. The factor model for x goes from x to x1, x2, and x3. Single-headed arrows. And notice that the first path is not going to be estimated, and the next two are. The first path has a value of 1, and the starting values for the next two paths are 0.1. Why do I do this? Well, this is one way to estimate or to identify a factor. You can identify a factor by fixing one of the paths to the indicators. That's not the only way to do it. You could fix the variance, but in this case, I would prefer to have the scale of the variable of the factor be set by this first indicator, x1. And that's a choice you get to make. I do the same thing to create the factor y. Three paths. The first one is fixed. The next are estimated. Same for z. Now for z, there's something we have to think about for the latent interaction. So we're predicting z using x, y, and the interaction. So there's three ways that we're predicting z. Should we ever fix the variance of z to be 1? No, because this is not the variance of z. This is the residual variance after these things are predicted. So we need to allow that to be able to be reduced when this prediction improves. If you fix this variance, then these parameters become very strange. It's always better when you are predicting a factor to identify the factor from the scale of one of its indicators. And that's a general purpose statement. It doesn't matter which program you're using. Always better to do it that way. Okay, so now I'm going to say, oh, I have some variance for x, y, and z. These are all going to be estimated. And I have some residual variance for each of these for x, y, and z. And then I have a covariance between x and y. This is covariance because it's arrows equals 2, and that's estimated. Notice that this is an aside, but at this point, there's probably people are going to say, well, how do I know what to use it for starting values? Well, so in general, I set the starting values for variances to be higher than the starting values for regression coefficients. In general, that's good. I try not to set anything to be exactly 0. So starting value of exactly 0 is just hard for the optimizer to figure out what's going on. It can be a singularity. So that's just to start out with. And okay, probably not a good idea to set your variance starting value to be a negative number either. But that goes without saying. Well, why do we do this? Why do other programs don't make me do this? Well, there's something called a local minimum that can happen in more complicated models. In some complicated models, there can be local minima that the optimizer will get stuck in. And you can think of the likelihood surface as this convoluted surface that, yes, it may be just one big valley, in which case, no problem. No matter where you start, you will walk downhill to be at the lowest spot, at the minimum. Okay, that's really good. But if there's a local minima, then you might get stuck in a local minimum, and you'll get a different answer if you start from a different spot. And we think this is a philosophical statement from the OpenMx developers that it's important to use multiple starting values. Once you have a complicated model that is you're trying to get to an answer, it's important to use multiple starting values and reassure yourself that you get to the same ending value all the time. If you get multiple ending values with multiple starting values, then there's a problem with your estimation. There's probably a problem with your model or your data. And there are several different kinds of problems that can happen. One of which, the most common, I think, is that there's the local minima are all on sort of, you've come down a surface and then there's a flat spot where there's many values that are all about as good as each other. And this means that the standard errors that are reported by every program's report standard errors, they assume a parabolic ending point, that you've got to a minimum that's a parabola. That is to say, the standard error on one side is the same as the standard error on the other side, negative and positive. It could be that there are asymmetric standard errors. And probably you want to use, if you see this problem, in fact, I would always use confidence intervals rather than standard errors when I report my final model. This is a function called MXCI that creates likelihood-based confidence intervals, which have the opportunity to be asymmetric. And they become wider if you've got a flat spot, and because they're not assuming a parabola. If you've got a flat spot in your likelihood space, the likelihood or the likelihood-based confidence intervals will get wider appropriately. And so this is this is an aside. It doesn't have to do with products of variables, but I think it's an important point. So that's why we insist that you pick some starting values. In fact, when I'm near the end of fitting a data set, frequently I'll put a little, I'll use the rnorm function in R to sort of wiggle the starting values a little bit and see if I'm getting the same answer, or if the program is, or if the likelihood space has multiple minima. There's an automatic function to do that in OpenMx, and it's called MX try hard. And what it does is it tries to find solutions, and it uses if it finds a solution, it jiggles the starting values and sees if it will come up to the same place again. So I would recommend using MX tryhard at the end once you've got your model running. Even if it goes, runs really fast, it's a way to feel better about the answer that you're getting. And so many times I've been asked, well, why do I get a different answer in OpenMX and Lavon or M plus? And oftentimes the answer is actually, these are two different. These are due to the starting values, and the starting values are picked automatically in those two programs. Okay. So we've created a model that has an interaction term latent, and this is an interaction between two latent variables, and it's basically as easy to do as a model that had just covariances between the three latent variables. Okay, you could see that this took a little longer. There's quite a few parameters here, 24 parameters. I mean, it's not 300, but it's a few. And it took a little while. Okay, so let's continue on with this script and ask, well, what happens if I remove that interaction term? And now I can compare those two models. And yes, our differences in log likelihood is 47, and the expected, the 95% confidence interval and according to the chi-square distribution for 1 degree of freedom is 3.8. So 47 is much larger than 3.8. And thus, our p-value is very small. It's unlikely that these two models fit as well as each other. Okay. Moderation, here's a latent moderation. Notice that I think this is interesting because, I thought about moderation as being very different than interaction. Before I started this, kind of diagram, and now I see that, latent interaction is exactly like moderation, but with one less path. And you can, you know, you can do the algebra and see that it's the case, but it wasn't so obvious to me until I saw the diagrams that moderation and interaction are almost exactly the same thing. You can square a variable. How do you do that? Well, you use this thing called a dummy variable. That's a latent variable with no variance. Notice that there's no double-headed arrow on this thing. Recently, I've been starting to use a plus sign in there and call it an addition node. And what that says is I'm going to take x and send it in to this product, and I'm also going to put x into the product. So x is coming in both sides of the product this way. And this is a trick just because we're creating an A matrix someplace, and so there's not room for two different paths going from X to this product node. So we can create another row and column in the A matrix by creating a dummy variable. There's no entry for it in the, or zero in the S matrix. That is to say, it has no variance. And then X is just passed through. And that gets to be X squared. Okay. You can go to the squared product if you like. But I think we should either, I think maybe let's take 5 minutes, and then we'll come back for the multi-group section. And any questions at this point? Just type your questions in. Okay, so in that case, let's take 5 minutes and come back at 20 after 11. Okay, we're back. And now for the sprint to the end here on multigroup models. Right. So why do we use multigroup models? We may be interested in group differences. That could be different demographic groups, or it could be a control versus an intervention group. Also, you may want to account for within group dependency. For instance, nested groups. Some people use multi-group models to test for factor invariance. I think this is a good use for it. You might be testing for experimental replication. Um, uh, you may you may have targeted differences that you're interested in. So variance or covariance group differences. You may want to freeze some things and fix others. You may have known parameter differences between groups. For instance, uh, uh, dizygotic versus monozygotic twins. So here's how we do it. There's two ways to test for parameter equality in two groups. Um, One way is to just use a moderator, just like we did before with the previous models. You could build a data set with a binary variable for group membership, and then use that binary variable as the moderator. Um, and this will test whether a moderation, that is to say, group difference, improves the fit. If the parameter is different in the two groups, then the moderator parameter will be significant. However, this method only works for two groups, and once you start to have a whole lot of moderation, it gets complicated fast. And the multi-group method splits the data, so there's a data frame for each group. And you can do this, just outside in R. Well, that'll be in our script. Now you split the data so that there's a data frame for each group, and then build the same model for each of the groups. And then fit a model where parameters are constrained to be equal or released. And you can, you don't have to have just two groups in this case. You can have multiple groups. You can have nested groups. These are all possibilities. So the moderation method, how does this work? Well, suppose we go back to our bivariate regression, and now we just are essentially multiplying by this group membership. And you can use the definition variable version of the of moderation, or you could use the products of variables. Usually, when it's group, the variable is the group, or this column is the group, that there's not missingness in that column. If you have missingness in the grouping, then maybe a multi-group is not the way to go. Maybe you're going to need to do something different. Group membership should be known when you have a multi-group model. So okay, so here's the possibility for the moderation method. Yeah, and I can show you this really quickly. This is very similar to what we saw before. Uh, and oh, this is two group. Where's the moderator version of it? Ah, here it is. Okay, so here's the moderator, and it's this is the variable. Now we have two dummy variables. We're going to have direct effects B1 and B2, and then from dummy to Y. Notice that dummy 1 to Y. This is free equals false. There's a one-headed arrow, and in the labels we put data dot and then GRP, where GRP is the grouping variable that we had in our data. And let's read the data in so you can see how this worked. Once again, in order to use this kind of method, we need to have a grouping variable. So which group do they belong to? In this case, it was just 0 or 1, depending on which group they were in. And we can see there's considerable differences in the correlations between the variables depending on which group they're in. But this is the trick right here, this line right here, and the same for the other one. This is pretty straightforward. You put data.group in one of the arrows going into, and this is for the means. So now we have both the regression and the means are potentially different across the groups. And yeah, and then we're just going to remove the moderator and see if there's a significant change. But this is basically the same as we saw before in the products of variables, but we're just using an older method, this definition variable method, which when you've got complete data, the products of variables and the definition variable method produce equivalent answers. Okay. So and that was this model here with the moderated means. But let's try it with two groups, two different models that are applying to each of the groups. So what are we going to do? We're going to set up one model that is we'll set up say the control model and the intervention model. And they will be just the same. They are free. They're not constrained. They could be anything. Each of the parameters could take on separate values for each group. And then we put those two child models inside a parent model. And the parent model has a fit function called multigroup. And inside the multigroup, give the names of the two submodels. So there's our parent model, and it's a very simple parent model. All it does is it adds up the function values for the two models, the two group models within group models. Okay, so here's what it looks like for our simple regression. We've got these parameters, and every one of them is potentially different. There's a CB2 and an IB2 for the intervention and the control group. There's a CB0 and an IB0, and so forth. Each one of them is potentially different. And then we'll start making constraints. First, we'll constrain, and this is up to you. This is what makes sense to you. It may be that we think it's most important that these two groups have their B1 parameter the same, or it might be that the B2 and B1 are the same. And how does that look? Well, okay, so it's really small here, but B1 and B2 are being constrained to be equal because their labels, B1 and B2, are the same across the two groups. And so within each model, the name is the same. And since they're in a container model, in a parent model, they all have the same namespace. So B1 here has got to be the same as B1 there. And finally, I mean, we could constrain everything to be equal. So now all of the values or all of the labels that are could potentially be different are equal to be the same. The means down here and the covariances as well. So let's fit this. Let's go and specify it and fit it. There it is. So I'll start out by reading in the data and describe it. So we've got 4 variables, x1, x2, y, but also a grouping variable. And here's how we split the data sets apart. We use lapply on the split function well, this is just to give us descriptive statistics for the two groups. And now we'll create a list that is a split of the two groups on the grouping variable, and we'll make the intervention data that the list that has 0 and the control the data that has a grouping of 1, the grouping variable of 1. So this is a way to split your data into separate data sets. So now what I do is I create a prototype model. That is to say, a model that would be the same for each of the groups. what is this doing? This is a RAM model. It just has manifests, and there's two regression predictors. There's a covariance between X1 and X2. There's excuse me, there's variances for the manifest variables, and there's means for the manifest variables. Okay, now we're going to create the prototype model, or I will create the intervention model, excuse me, by taking the prototype. Notice the prototype does not have a data statement in it. There's no data. There's just all of the paths and everything are there, but no data. So now we're going to add the intervention data to the intervention model, and we'll add the control data to the control model, or add it to the prototype model and it becomes the control model. Add the intervention data to the prototype model and it becomes the intervention model. And notice we've got names for each of these. But notice that because I used the same prototype model for both of these, all of the parameters are constrained to be equal because all of the labels are the same. Now here's where we create the parent model. Some people call it the container model. We call this the two-group model fixed. Its name is two-group model fixed. And it has in it the intervention model and the control model. It also has a fit function called multigroup, which says use intervention model fixed, which was the name that we created up here, and control model fixed to calculate the fit function, which is just the sum of the fit functions of the underlying groups. Okay. Now notice that we can, this may be the first time we've used the ref model. So there's this function called ref models. And what it does is once you've run a model, you can ask for its ref models. That is to say, the saturated model and the independence model. And for most MX models, exception being products of variables, MX ref models will calculate the saturated model and the independent model and set them up so that you can say T-ref models equals this model that you calculated. And what that does is it sets up a saturated model, runs it. Sets up a independence model, runs it. Saves the parameters or the fit functions that it needs so that you can get your summary out. Okay. So here we go. So here we have it. We have the same B1 in both groups. So up here, same B1 in both groups, same B2 in both groups, same variance of X1 and variance of X2 and covariance and everything. Same means. because we use the same prototype model for both of these. Okay, well, what about everything being free? So here I'm going to create an intervention model that has an I after each of those parameters. So the labels all get a little I after them. And here in the control model, the labels all get a little C after them. So now the labels are different in the different groups. And what that means is when I define these models and then add them into a container model and ask for a multigroup fit function and run it, and notice that something's interesting here. Notice I've got the same ref model for this as for the previous model. Yes, it's the same data, it's the same model, it's just the parameters are different. And so the independence model and the saturated model will be the same as they were before. So I don't have to run it again. And, that may not seem like a lot here because because the models are running so fast. But I'll tell you, when you start to have more complicated models, the saturated model in particular can take a very long time to run. It may take, hours to run. And so it's good to just save the results from that, and then you can use it in summaries as you're going along. Okay, so now I've got a separate B1 and B2 for group 1, the intervention group B1 and B2, and the control group B1 and B2. So control group B1 and B2, well, they're somewhat different values than each other. So B2 is quite a bit different, actually, in the intervention and control group. So here, next I'm going to take the model free, and I'm going to just constrain B1. So B1 is the only thing that's going to be the same across the two groups, and everything else can vary across the two groups. So there's only one B1, but there's two B2s and everything else. Here I'm going to constrain just B2 to be the same across the two groups. And I'm not going to really look at all of this stuff until, here I'm going to constrain B1 and B2 as well. But now I'm going to MX compare just I start with the free model, and I'm going to compare each of those other models that I fit to the free model. How much worse did each one of those fit than the free model? Now notice that this is not accumulating across. We're not comparing B1, this two-group model B1 to two-group model B2. We're comparing each one of them to the reference model, which is the free model, the one that has the most degrees of freedom, or excuse me, the most estimated parameters. And you can see that it doesn't, we could constrain B1 to be the same across groups. And yeah, we haven't lost a lot of fit. But if we constrain B2 or B1 and B2, then we've lost a lot of fit. A significant amount of fit has been lost. And the same goes for everything. If we constrain everything, that's 9 degrees of freedom and a loss of fit of 18 log likelihood points. And there's different ways that you can do comparisons. Notice that, I should say, notice that just constraining B1 or just constraining B2, you cannot compare the two of those. And the reason is that these are not nested. The comparisons that we're making here are nested comparisons. That means that either you're only, well, in this case, you are only constraining parameters, only constraining. So you can compare between the free and this B1 because you're only constraining between everything free and this. You're only constraining. Each time comparing back to the original, you're only constraining. But here, between constrained B1 and constrained B2, you're both freeing up and constraining. And, then the estimated parameters are the same. And then the chi-square test is not a fair test. So you must have nested models in order to make this comparison test. One way that I like to make this if I have lots of comparisons where I've released and constrained and so forth between different models, is to plot the fit statistics against the estimated parameters. And this is more of a it's not a statistical test. This is more of a graphical look at what you're doing, but it can be useful and interesting. So here I'm plotting that, plotting those fit statistics. So there's function values, and where is it? There it is. Why not? Oh, I see. I've not created these data objects to plot. Okay. That's better. So here's our log likelihood or our estimated parameters and the expected log likelihood loss. And each of those, here's our saturated model, and here's our independence model, the number of estimated parameters, and you can see, well, these models over here, they seem to be worse. This model here, it could be okay. Making that constraint probably is not hurting the model fit. Okay. I've got one more script to get through, and we've only got 10 minutes. But I'm gonna shoot for it. Let's see. And that is measurement invariance. So it's nice when latent variables retain their meaning from one sample to the next. How do they gain their meaning? They gain their meaning from the indicators. That is to say, the proportion of variance that is accounted for in each of the indicators by the factor should remain the same if the latent variable is invariant across groups. And we can test each of the kinds of invariance using a multi-group model. So here we've got no invariance. This is a model that is essentially exploratory factor analysis. So no invariance, could be anything. Configural invariance, that is to say, where the zeros are in the loading matrix is the same, but the values of each of the loadings could be different. And here we have partial metric invariance, that is to say the loadings are the same, but the variances and covariances between the factors are different. And actually, this is what I would shoot for. I'm not so worried that the covariances or the variances of a factor are different across groups, because this at least means that y here has the same meaning as the y here, even though the covariances might be different between these. Or, there might be more between person differences in y in group 2 than in group 1. Well, at least y means the same thing in both of them. Now, you can go further, though, than that and ask for complete or full or strict metric invariance. That is to say, all of the variances and covariances between the factors are the same, as well as the loadings. And notice that I'm only releasing constraints. I'm only applying constraints. So that means that these are nested, these tests are nested within one another. And so it's fair to make a chi-square test between the fit statistics, the fit functions of these models. So metric invariance script is over here, and I think I'm going to instead ask if there's questions. We've only got 5 minutes. Only got 5 more minutes here. so that so for questions. If there's no questions, I'll go through this script. But I thought so how did I make these path diagrams? I use a program called OmniGraffle. And it's relatively inexpensive for academic use. Um, uh, so, you know, I hate to be selling software here, but I use it for everything. All of my diagrams, and lots of the publication diagrams that I make that are not path diagrams, but other kinds of diagrams. And if you decide to use that, I have a template of it's sort of a template that lets you draw these very quickly, and I'll send that around to the mailing list in case you want to use that. Yeah, okay, so there is no, so subtraction nodes are really easy. All you have to do is on the way into the addition node, use a -1, and you get a subtraction node. But division nodes are more difficult, and we have not implemented division in OpenMx yet. We are also looking into other function nodes, exponential, power function, the ReLU function in case you would want to be doing some machine learning with OpenMx. So yeah. Okay, well, I guess that's the end of today's workshop. Thanks for attending. I'm glad to have the opportunity to talk to you. And you can always email me. I'd be happy to take questions over email.
Thank you, Dr. Boker, for this amazing lecture, and thank you all for participating in this workshop.